Double replacement reactions are the fifth and final reaction type that we're going to talk about. It's two compounds coming together, and so this is the only reaction of the five types where you have two compounds on the reactant side of the equation. So it's basically just, the formula is AX plus BY yields AY plus BX. So it's kind of like A and B are just sort of trading partners there. So you have A going with Y and B going with X. And you can think of it as A and B are both cations or positive ions. And that's how the new compounds are being formed. Now they're going to be with new negative ions or anions. Now, the note there, it says these reactions will not actually take place unless the product includes an insoluble ionic compound or a molecular compound. In other words, if both products are soluble ionic compounds, then no reaction takes place. And soluble versus insoluble simply means, does it dissolve in water or does it not dissolve in water? Soluble means it does, insoluble means it doesn't. So let's take a look at an example and talk about what this means. So if I have, for example, and of course you should write this example down, barium chloride, BaCl2, and our reactants are always going to be aqueous, meaning dissolved in water. And I'm going to react that with silver nitrate, so again also aqueous. And if I just sort of identify my positive ions, it's going to be barium and silver. Okay, it's always going to be the first thing. It's usually going to be a metal, although it could be ammonium or it could be hydrogen. But in this case, it's two metals, and they're just going to trade places. So barium, instead of being paired with chloride, is now going to be paired with nitrate. So I'm going to get as one product, barium nitrate. And because of charges, it's going to be BaNO3 because barium is +2 and nitrate is -1. And then I'm also going to get silver paired with chloride. And again, because of charges, silver is +1, chloride is -1. We don't need any subscripts there. Okay, so then this business about figuring out whether it's a reaction or not, we're not using the activity series with double replacement like we did with single replacement. We're looking at solubility. So both of our reactants were aqueous. The question is, will both of our products be aqueous? Because if they're both aqueous, then that simply means that no reaction has happened. And I'll talk about why that is here in just a minute. So let's take a look at each one and talk about how to determine that. We're going to use this little table at the bottom of your sheet. And so basically what this is telling you is for compounds that contain these ions, like for example, if a compound contains nitrate, the rule is that it's always soluble because it says solubility, soluble, exceptions, none. So everything that contains nitrate is going to be able to dissolve in water pretty much every time. The same thing is true with acetate, but you can see as we go down the list, we have some different rules. And you don't have to memorize these rules. These are always going to be provided for you. So let's go back up to our example reaction. One of our products is barium nitrate. Well, we just said that the rule for compounds that contain nitrate, such as barium nitrate, that those compounds are soluble and that there are no exceptions. So if it's soluble, that means it can be dissolved in water, which is exactly what aqueous means. It means dissolved in water. So one of our two products is aqueous. The other one is silver chloride. So what we're going to have to do is look at our rules, and we're always going to, or almost always going to go by the negative ion. We just looked at the rule for nitrates. Well, silver chloride, the negative ion is chloride. So I'm going to find the rule for chlorides, and there it is. It says chlorides, along with fluorides, bromides, and iodides, are soluble, but there are three exceptions. In other words, what this is telling us is if I had silver paired with chloride, then that is an exception, and so therefore it is not soluble. Okay? But if I had sodium paired with chloride, well then that is that's soluble because sodium is not one of these three exceptions. But silver is. So what this means is for this particular reaction where we're making silver chloride is insoluble because silver is one of my three exceptions to my rule that says that chlorides tend to be soluble. So if it's not soluble, the physical state is going to be solid. That means it forms a precipitate, basically like a powder that won't dissolve. So you're putting together these two aqueous solutions and you're getting one that's aqueous and one that's solid. And that's how you know you have a reaction. Now we should also balance, and it looks like we have two nitrates on the right, so I'm going to put a 2 in front of silver nitrate on the left. And to balance the silvers then, I'm going to put a 2 in front of silver chloride, which also gives me two chlorides, which matches the 2 chlorides on the left, and barium is already balanced. So that's a balanced equation. So let's talk about why this is a reaction. If I were to draw this out, let's say I have a beaker, a small beaker that contains some aqueous barium chloride. Okay, so there's my beaker. And I've got another beaker that contains some aqueous silver nitrate. Okay, and I'm going to use some colors just to sort of symbolize. Let's say barium is purple, and I'm going to make chloride red, and we'll make silver over here is going to be symbolized by these little blue dots. And let's say nitrate is, let's go with orange. Okay, so each of those aqueous solutions contains these particles. So if it's aqueous, that means it's dissolved. So if I have barium chloride aqueous, that means that the barium ions and the chloride ions are separate. They're dissolved. They're surrounded by water molecules. So there's water in between those ions. And the same thing is true for my silver nitrate. So silver is blue, so I would have a silver, and then I would have an orange nitrate over here kind of by itself, right? And so, again, aqueous meaning dissolved, split up, surrounded by water. Now, when I put these two together, I'm going to have to use a bigger beaker. So when I put these two together, the barium and the nitrates are still aqueous. So what that means is my purple barium is still sort of floating around on its own, surrounded by water molecules. And my orange nitrates, which are, orange, so they're kind of separate over here. And I should balance and put in the right amounts of each one, but you get the idea. The idea here is the barium nitrate is aqueous, meaning that the ions are separate from each other. I'll go ahead and put in 2 nitrates just to match the subscript 2 up here. Anyway, so going to our silver chloride then, it's actually solid. And so what that means is my blue silver ions and my red chloride ions are not just sort of floating around independent of one another. They are actually stuck together to form a crystal. And that crystal would just be a bunch of positives and negatives stuck together. And we call this a precipitate because usually once they stick together, they're heavy enough that they sink down to the bottom of the solution and form a cloudiness or a solid crystal. Now, if I look at another example of a reaction that maybe doesn't work, let's say we got NaCl, aqueous, reacting with, let's go with potassium acetate, also aqueous. And so my sodium and my potassium trade places, and I get sodium acetate. And that's correct in a 1-to-1 ratio because, sodium's +1, acetate's -1. And if I look at my rules, the rule for acetates is that they are soluble and there are no exceptions. So right away I know the physical state for sodium acetate is aqueous. And then my other product, the potassium, is going to be paired with chloride. So KCl is also aqueous because if I look at my rule, chlorides are soluble and potassium is not one of my 3 exceptions. So it would also be aqueous because it's soluble. So what this means is, if I were to think about, and I'm not going to draw everything, but if I were to think about what a beaker of aqueous sodium acetate and aqueous potassium chloride would look like, well, all I'm really doing is taking these ions that started out separate from each other and putting them in the same beaker, but they're not sticking together to form a solid precipitate like the silver chloride did. And because they're not doing that, all I'm really doing here is mixing together these 4 ions that were previously, separated in groups of 2, sodium chloride and potassium acetate, and they're now just all in the same beaker. But that's not a chemical reaction, that's just a mixture. And so because I got 2 aqueous solutions, it's not a reaction, it's just a mixture. So we would say NR, again, because my 2 products both turned out to be aqueous. Now the natural question is probably going to be, well, what if you get 2 solids? You won't get 2 solids. It's always going to either be aqueous-aqueous or aqueous solid or solid aqueous. You're going to get 1 solid or you're going to get no solids. And if you get 1 solid, it's a reaction. And if you get no solids, it's not a reaction. So let's try one that you can try to predict on your own here. Let's go with lithium sulfate reacting with strontium hydroxide. Okay. So go ahead and sort of predict what products you would get, and then also decide if it's a reaction or not. Okay, so we should have said, and the order doesn't really matter, but you should have said lithium would be paired with hydroxide, and that's going to be 1 to 1 because lithium is +1 and hydroxide is -1. And you should have said that hydroxides are insoluble, but lithium is an exception. So that means that this is soluble, which means aqueous. And then the other product would have been strontium paired with sulfate. And strontium is +2 and sulfate is -2. And sulfates are generally soluble, but strontium is an exception. That makes this one insoluble, which makes it a solid, which means this is a reaction because we got a solid precipitate. We have one product that looks like this. It's a crystalline solid where the stuff is coming together. Then we just have to check the balance. It looks like hydroxide. We only have 1 hydroxide on the right, so I'm going to go ahead and put a 2 there. So I have 2 hydroxides on both sides. That gives me 2 lithiums, and I have 2 lithiums on the left, 1 sulfate, 1 sulfate, 1 strontium, 1 strontium. So it looks like I'm all done.